Okay, we just needed some time, change the laptops, but Ralf is ready now. So next talk, I think, will also be very interesting. We can always go back to the keynote today because Sergey already talked about return-oriented programming. So now we will get some new information about return-oriented rootkits presented by Ralf Hund. He's from the University of Mannheim. Working there, and I think he's working on some kind of defense strategies and all that stuff, and so he's also looking for new attacks that can be done against software devices and so forth. So please, Ralf.
Yes, thank you for the nice introduction, and welcome to my presentation about return-oriented rootkits. As Michael already said, I work for the University of Mannheim right now, where I'm a PhD student. And what I'm going to present you today is actually what I researched when I wrote my diploma thesis 1 year ago. And today I'm going to show you how return-oriented programming works, what's it all about. So that's the first part of my presentation. And once we've done that, we can dig into certain domains in which we need this kind of new attack to bypass certain protection schemes. So I'm pretty sure that many of you have already heard the expression return-oriented programming, especially after it was presented also in the keynote today. And it's a pretty high topic that was discussed in many presentations on past year's security conferences, such as Black Hat or DEF CON. And in the beginning, it all started in 2007, where Hovav Shacham wrote his paper, The Geometry of Innocent Flesh on the Bone, Return into libc without function calls. So, as always, some crazy hacker dudes had already had similar ideas beforehand, but let's just say that this was kind of the beginning of the entire hype about return-oriented programming. So, if you would ask me what return-oriented programming is all about, I would say that it's about how to write programs that do not have any own code. Until a few years ago, everyone had this assumption that if you would want to execute your own computations on a computer, then you would need to have your own code that you inject into the system and execute it in some way. But this was kind of the first time that we really saw that this assumption is not kind of true. And especially from the security perspective, this is problematic since many protections rely on this certain assumptions. So instead of using our own code in the system, instead of injecting our own code into the system, we just abuse already existing code that is spread all around the main memory, and we try to chain this code together to make it do arbitrary stuff. And when we mean arbitrary stuff, we usually mean malicious stuff. So before I tell you how return-oriented programming actually works, it might be wise to take a look back into the history of software vulnerabilities, especially to take a look on what I call it, king of software vulnerabilities, which is the buffer overflow attack. The buffer overflow vulnerability, which posed a lot of headaches to many security researchers, as it is, I would say, still one of the most widespread vulnerabilities that you can find in software, since most of the software that you run on your computer is still written in C. And as we all know, C is a non-type-safe programming language, which also means that it does not have any implicit data bounds checks. And so the idea about buffer overflows is simply that we abuse these missing data bounds checks to overrun certain buffers, and then we can also override function references that are somewhere in the memory, and hence we can divert the control flow. This is actually what most of the past worm mass infection waves that we saw used. So the plaster worm, for example, used the buffer overflow vulnerability, the Sessa worm did, and many others also did. Looking at my very basic and schematic animation about how buffer overflows work, let's assume we have a bad boy on the left side who could be, where can you see my mouse? Oh yeah, who could be, let's say, a worm or some actual hacker dude who tries to infect this web server. So let's assume we have a web server on the right side, which runs some web server process. And as we all know, this process is loaded into memory when it is executed. This program is loaded into memory when it is executed by the operating system. So we have some sort of main memory on the right side with a data section which holds all the data areas which we need to process requests and do the computations. And we have a code area in which we simply keep our code. So let's assume an attacker sends this HTTP string, which has some sort of included shellcode. He sends it as a packet to the web server. And of course, the web server needs to process the request and hence put this data somewhere into memory. So we end up with custom data which can be controlled by an attacker, which is in the memory. And let's just assume that some sort of buffer overflow happens while processing this request, which means that the attacker is now able of diverting the control flow. And what happens is that the CPU jumps somewhere from the code section into this data section. And from this point on, you're basically owned because now the attacker can do whatever he wants in your system. So having talked about buffer overflows, we naturally have to think about countermeasures. And as we all know, buffer overflows are just simple programming errors. They all stem from the fact that in the end, we have some humans who program our code, and humans just do errors, especially when they are under pressure, which is happening all the time when you work in a productive environment where you have deadlines to which you have to stick to. And so one idea might be to simply educate programmers, which is, for example, what Microsoft does when you call certain possibly unsafe functions in there with their C compiler. It prints out a warning which says that please don't use this function, use our super safe other function instead. And of course, what I do and what I think most of the other programmers also do is the first thing I do is I disable these warnings because I definitely do not want to tell anyone, I do not want to be told which function I should use and which functions I didn't use because I kind of grew up using these functions. And also, if I want to have portable code, then this can be kind of problematic because most of these secure functions are not portable among other operating systems. So this is maybe a bad idea, and a more appealing approach might be to simply find technical solutions. So why should we rely on humans which are bound to do errors when we can simply find a technical solution that will fend off any buffer overflow attacks? So there were some smart suggestions by many people on how we can defend ourselves against buffer overflows. There were these heap and stack cookie protection types in which you put some random value between function references in memory so that you can detect when things were overwritten and function references are being tampered with. There were also control integrity type of protections, but in the end, they all have the shortcoming that they have some impact on performance, some negative impact on performance, and you definitely do not want this to happen. However, there has been one promising approach, which has also been introduced in the keynote, which is the non-executable approach. And the idea behind that is kind of simple, because if we look again at our memory on the right side, then we can see that this is just a very simple schematic figure of how the memory looks. But as I said, we have some sort of data region, and we have another code region in which we keep our code. So why would we want to let the CPU execute code from a data region which can't possibly be meant to contain any code? So in, let's say, 99% of all cases, you do not have to have an executable data region because you do not have any code in your data region. And so why do we allow the CPU to do that? There are some exceptions to this rule, such as just-in-time compilers, and this is actually why Java does not have such protections implemented, but that's another topic. And as I said, for 99% of all cases, it is not necessary to have an executable data section. However, there is still some kind of silly problem, which is that traditionally on Intel, it is just impossible to do that. We cannot tell the CPU, if we only use the MMU paging mechanisms, we cannot tell the CPU to mark a memory region as readable but not executable. And you definitely want your data section to be readable. So there was nothing we could do until a few years ago when Intel and AMD foresaw this problem and introduced the so-called XD and NX bit. This is basically the same. Intel just calls it another way than AMD does. So when Intel and AMD introduced these bits, it was actually possible now to mark certain regions to be non-executable. And this is what also is called the WXORX approach, which means that you can't have a memory region which is writable and executable at the same time. So what do we do now? Attackers can still inject their code into memory. However, when they want to execute their code, this gets detected by the CPU and some sort of exception is thrown, which means that well, this is not a perfect solution because we still have the programming errors inside our code, but we can still, at least we won't get owned because an attacker won't be able of executing his own instructions. So it is likely that the process will still crash or has to restart or stuff like that, but at least attackers can do whatever they want on our PC. This seemed to be a kind of promising approach, and that's also why it was implemented by Microsoft as the so-called data execution prevention, which you probably heard of, DEP. It was introduced in Windows XP Service Pack 2 as an opt-in feature, which means that you would have to explicitly enable it if you would want to use it for a process. And since Windows Vista 64-bit, it's an opt-out feature, which means that you have to explicitly disable it. And every process runs with DEP by default. I will stick to Windows in the following because it's the predominant system, especially for malware. And however, there are other operating systems such as Linux, BSD, macOS have also implemented similar techniques. So non-executable stack has already been implemented for many other operating systems. And in the end, they all rely on this non-executable bit provided by Intel or AMD. So the question now is, are our problems really solved? And as you can imagine, of course the answer is no, because my talk is not going to end here. So the intuitive idea now that attackers have gotten, and that's, this is a kind of idea that everyone that just thinks about the problem that we now have, will get. And the idea now is that instead of injecting any own code into the system, why don't we just abuse existing code in the system? Because we have plenty of code lying around somewhere in memory, because we have libraries which are loaded into memory, such as the C standard library. We have operating system libraries loaded into the system, and we also have the program code, which is somewhere in the memory. So what if we just abuse this code to let it do the dirty work for us? And to show you how kind of easy this is, why don't we just take a look at the so-called system function. If you have already programmed in C, you might know what it does. For all of the others, it's a kind of simple function which is provided for all C systems. And what it does is it takes one argument, which is a normal string, and it then executes the program or the arguments provided in this parameter on the shell. So if you're on the Linux system, all it does, it just takes this argument and executes a bash or whatever shell with it. So let's assume we have this system function somewhere in memory. We know where it is. Instead of injecting our own code into the system, we could simply just provide only the parameters, which is in this case a wget-badboy.org/baud, point.baud, which, as you all know, just downloads some binary from the web and executes it. And if we provide this parameter somewhere on the stack, let's say, and only jump to the system function, then what will happen is it will get executed, and all of the protections such as DEP won't get any notion of that because we did not provide any code. We simply provided a simple data string. And so in the end, what we are capable of is we can execute arbitrary binaries nevertheless. So DEP is completely useless in this case. This is what actually is called the return to libc attack. So once we once we know what return to libc is, we are not far away from return-oriented programming. This is just some sort of advancement of return to libc. And as I said, in return to libc, we look at functions, which means that we can execute arbitrary existing functions to do all the work for us. And now in return-oriented programming, we shift from functions to certain instruction sequences. So instead of jumping to functions, we jump to certain instruction sequences, and we try to chain these instruction sequences together to sequentially execute them. And the idea is that if we have enough of these instruction sequences, so let's say we have an instruction sequence that can perform an add operation, and another bunch of instruction sequences that can perform a multiplication and all stuff like that you can actually need in a processor to implement high-level languages. When we have enough of these instruction sequences, we can actually do arbitrary computations, which means that we are as powerful as any other compiled code. The only requirement that we need to have is we need to control the stack, but we can do that anyway if we have a buffer overflow vulnerability. And even if you have a heap overflow or other vulnerability, there are still always ways in which you can finally own the stack. So now I'm going to show you how it actually works on your computer. Before I do that, I just have one small slide that explains how code gets executed on an Intel x86 computer. So as in every other architecture, we have one instruction pointer by the name of EIP in this case, which points to the current memory instruction. So in this case, we have EIP pointing to some random instruction that I simply picked from some random binary. It points to move EAX, some stuff. And when this gets executed, the instruction pointer increases, points to the next instruction, and so on and so on. So we have a sequential execution of instructions in the normal case. You could have a jump instruction between there, but this is how normal code gets executed on your computer. So when it comes to return-oriented programming, things are a bit more different. So this animation should give you the big picture on how it works. So let's assume we have a vulnerable function which has a buffer overflow inside, and this function gets called, and some nasty hacker tries to exploit a vulnerability in order to do a return-oriented attack against the system. So we have the vulnerable function on the left side with the instruction pointer pointing to the prolog. On the right side, you can see the stack area, which is uninteresting at this stage. So let's assume the instruction pointer finally comes to the buffer overflow. The buffer overflow happens, which means that we now are in charge of the stack. Since we can override, let's say, arbitrary information on the stack, in this case, we overrode the return pointer of the subroutine call, which now points to the instruction sequence A. So this is the memory address of this instruction sequence here. And this is the memory address of this instruction sequence, and so on. So until the vulnerable function returns, nothing happens. But if it reaches the standard return instruction from x86, it will then load the value of the data being pointed to by ESP into the instruction pointer. So what we have is we have the stack pointer pointing to that modified stack area, and this value now gets loaded into the instruction pointer, which means that it moves along to our instruction sequence A. Some instruction A gets executed. We have the next return sequence, the next return instruction. This already shows you how these instruction sequences look like. They all end in a return instruction. So when we have another return instruction, the stack pointer was automatically increased, and we now point to the instruction sequence B, which means that now B gets executed, the next return instruction comes, and so on and so on. So this is how return-oriented programming actually looks like in your PC. If you would debug a return-oriented program in the debugger, then this is what you would see. So to summarize, controlling the stack is absolutely sufficient to perform arbitrary control flow modifications. And if we have enough of these useful instruction sequences, we can even do arbitrary computations, and we are just as powerful as any other normal compiled program would be. So this is kind of where I started my work, because what I showed you had already been researched in this first paper that I mentioned, where Shaham manually simply scanned an existing C library for Linux and searched for these instruction sequences. And what he did was he just loaded it into his disassembler and looked for an instruction sequence or a bunch of instruction sequence that would let him to perform an add addition, that would let him to, let's say, modify the stack pointer, because we need that to implement return-oriented jumps, because in our situation, the stack pointer adopts the role of the instruction pointer and stuff like that. So he really just sat down and looked at a specific C library to do that, and his result was that the code of one libc library, which is around a few megabytes, was sufficient to allow for arbitrary computations. And furthermore, he also introduced the name gadget, which is nothing but a return-oriented piece of code that performs a specific task. So I will use this name on the next slides a few times. So a gadget is, let's say, a bunch of chained together useful instruction sequences that can add two variables or, as I said, modify the stack pointer. So this is where I started my work, and the problem at this stage kind of was that it was all proven to work in theory. So it was proven that, as I said, libc had enough instruction sequences to do that, but no one had ever showed that this actually works in practice. And there really was no domain in which we really desperately needed return-oriented programming, because we could still do the standard return to libc type attacks. And for instance, if we want to attack a standard Windows process from the outside, which has DEP enabled, what we can do, for instance, is we can do a return to libc attack against a system function that is within the operating system that simply disables DEP. So the obvious thing that I would do if I was an attacker, I would simply just start with a return to libc attack, call this function, disable DEP, and from then on I can do whatever I want. I can still inject my own code. So this is kind of boring, because we don't need return-oriented programming at all. However, as it turned out, there are some situations in which it is really the only tool you can have to mount some certain types of attacks. And this is what I'm going to talk in the rest of my presentation. So let's do a little shift away from return-oriented programming into operating system security. And if you've already worked with operating system, you might know that operating systems separate your computer into two different parts, which is user land and kernel land. And the reason why this is done is simply because let's assume you start your Windows calculator and there is some programming error in your calculator, then you definitely do not want to let that programming error crash your entire PC. So you don't want to have a blue screen of death just because there was a division by 0 or whatever. And this is why the operating system separates the system in privileged and non-privileged areas. And non-privileged code, such as the Windows calculator, cannot access all of the memory regions in the system, and it can, for instance, not directly communicate with the hardware. That is the task of drivers and the operating kernel itself. So we have the operating kernel and a bunch of drivers which run with elevated privileges, which means that they can basically do whatever they want. And we have other normal code, normal processes that simply have certain restrictions in what they can do. So taking a look at this from the security perspective, we know that compromising of a privileged component in the system is some sort of worst case scenario, because when you manage to do that, you can now do whatever you want in the system, and you can do all the nasty stuff such as hiding processes, hiding network connections. In other words, you can really program a rootkit, which is some sort of ultimate attack against an operating system kernel in general. So some people thought about how we could defend ourselves against such attacks, how we could at least prevent attackers from executing their code in privileged modes, which means that let's suppose you have a buffer overflow within a kernel. That the idea was that even if you had arbitrary vulnerabilities in such privileged components, an attacker would still be unable to exploit these vulnerabilities to, let's say, install a rootkit. There were some papers about this issue. The two most interesting ones are, as I would say, first Nickel, and the second one was Segweiser. These are two programs which were programmed by the University of Purdue and Carnegie Mellon. And what they do is they all rely on some kind of hypervisor approach, which means that they have a dedicated component which is even above the kernel components. And from this hypervisor, they enforce two properties. One of the properties is the no overwriting of existing code property, which means that it is not possible for an attacker to overwrite privileged code in the system and then execute it, and it's also not possible to inject new code to some other area in the system and then execute it. So we are only talking about privileged code in this case. You can still do whatever you want in user land. And this allows for a kind of very interesting attacker model, which means that we can have an attacker which may have already owned everything in user land, which means that under Windows he can have administrator write privileges, and under Linux he can have root privileges. Furthermore, we allow arbitrary vulnerabilities in the kernel, and still under these two systems it is not possible for an attacker to attack the kernel itself. At least that's what they say. So in the end, both systems have some sort of whitelisting approach in which you simply specify the specific kernel and drivers which you allow to be loaded in the system, and everything else, any other code, is then prevented from being executed in your system. So let's just have a quick look on Nickel and to see how it works from a technical point of view. Nickel is an extension of the QEMU hypervisor, and which kind of means it's not a real productive system, but more a proof of concept system, because you need to have QEMU running and you need to have a completely emulated CPU for it to work. However, what it does is it keeps a copy of the entire physical guest memory. So when you have a Windows system running in QEMU, then it simply copies your physical memory inside the hypervisor. This copied memory is called the shadow memory, and it is not accessible from within the guest operating system. And what it does now is that every time when an instruction is being executed, it compares this instruction against its counterpart in the shadow memory. When both instructions match, then everything is okay, the instruction gets executed. However, if the instructions do not match, then it generates some sort of exception, and which could have been because there are two scenarios in which this might happen. The first scenario is that a new driver gets loaded, and when this is the case, it tries to authorize this driver just by computing a simple hash value over the code sections, and when this hash value is inside the whitelist, it just copies the code in the shadow memory and continues execution. In the second case, let's say an attacker injected code in the system and wanted to execute it. If this is the case, then the system will also try to authorize the code. However, you cannot have a matching hash value which is in the whitelist, which means that an attacker cannot carry out this attack. Nickel itself was implemented for Windows and Linux as a proof of concept system, and the interesting thing now is that we are inside a system in which we cannot inject and execute a single own CPU instruction. So a CPU instruction is the most elementary thing you can run in a computer, and in this case, if Nickel runs well, then we really cannot execute a single own instruction. And this is somewhat the perfect target for a return-oriented programming attack, because now we cannot simply do return to libc stuff and simply disable the protection, because the protection is within the hypervisor and we cannot access the hypervisor. However, now we can still try to mount our return-oriented attack. And that's what it was all about. So now we have our system, and in the beginning we have to think about which approach do we take to, let's say, program a return-oriented rootkit, because a rootkit is the kind of ultimate attack against the kernel, And what I wanted to do at this stage was I wanted to program a real return-oriented rootkit that runs under nickel or segweiser, just to show that these assumptions that they make can be subverted. What could we do? We could do the same thing that Howard Shaham did in his first paper, which is we can simply fire up a disassembler, manually scan existing code for these instruction sequences that we need, and then we can chain these instruction sequences together to form a complex rootkit that, let's say, hides a process or hides network connections and does all stuff like that. However, as you can imagine, I did not want to spend, let's say, 2 months on scanning code bases, because this is really time-consuming work and really boring and time-consuming work. And furthermore, there is also another problem, which is that let's assume we have done this attack against one kernel, against one PC, and it actually works. Then we cannot simply port the code that we have to another system, even if it runs the same operating system version, because you have a completely new set of drivers being loaded, which means there is other code which you might want to abuse for your attack, and also you might have a slightly different operating system version. So, for example, under Linux, when you have an operating system kernel for one distribution, then it's probably the code looks a bit different than in another distribution, because they have compiled it with different flags or put some other stuff in it. And that's simply because, that's the reason why this is some kind of bad approach. So what we need is we need to actually automate return-oriented programming, and we actually need some tools that do all the nasty work for us, so that in the end we can program a rootkit just as comfortable as we would program any other rootkit in a standard high-level language such as C. So just to repeat, we have two problems. The very varying environment of each system. Each computer has its own code base, and we definitely want to use as many instructions as we can find in the memory. And the second point is that there was no return-oriented compiler at this stage. There were only standard compilers that let you compile C code, but what these compilers do is, in the end, they all produce machine-dependent code, and that's definitely not what we want. We want to have some sort of compiler that generates the stack allocations that we need, so the return addresses that we need to mount our attack. And what we did is we created a framework that facilitated the development of complex return-oriented code. This framework consists of 3 major components, which I'm going to show you in the following. And it was implemented for 32-bit Windows operating system, since this is the predominant setting that you can see in the wild. So let's take a look at the framework overview. We have the first component, which is the constructor. And what the constructor does is it scans a given set of binaries for instruction sequences. So in our case, we just scan the operating system kernel, which is NTOS kernel.exe under Windows. It just lies in your Windows/System32 directory, along with the other drivers that are loaded in the system. So we just scan these files on the disk, such as the Win32k subsystem driver, or the file system drivers, and whatever drivers we can find which are loaded in the system. The constructor searches for these instruction sequences, extracts them all, and what it then does is it tries to automatically compute a certain set of gadgets. So let's say we have a well-defined set of gadgets. We need one gadget to perform an addition between 2 variables. We need one gadget to perform a division between 2 variables, because we later need that to implement our high-level language. So the constructor, it works with some heuristic, which I'm not going to show because it might be a bit too complex. But in the end, it has some certain heuristics, because certain instruction sequences can be found quite often in the code. Others can't be found quite often in the code. And it always tries to emulate additions, or let's say, for instance, you can emulate a multiplication once you have an addition and a loop and stuff like that. And the constructor tries to do that actually as good as it can. So the output of the constructor is a list of gadgets, which was constructed from the given code base. And these gadgets are then taken as an import along with a high-level source code file written in a dedicated language into the compiler. So we have our own dedicated high-level language, which is very similar to other high-level languages, which really allows us to program just as comfortable as we would program in, let's say, C. You can see this in one of the examples, which I'm going to show you on the next slides. So this was the second component, the standard compiler, and in the third phase, we have the loader component, which is nothing but a library which is supposed to be linked against an exploit, because at the stage of compilation, we do not know the final memory addresses to the instruction sequences. And this stems from the fact that every driver gets loaded into your main memory, of course, when you boot your system, and it is loaded to a certain base address, and this base address can change whenever you reboot your system. It depends on the order in which you load your drivers, and we really need these base addresses in the system, because otherwise we do not know the final memory addresses where we can find the instruction sequences that we want to jump to. So what the loader does is it patches the compiled code, and simply adds the base addresses of all the loaded drivers. So here we have an example on how a gadget might look like. Let's say we want to have a gadget that performs an AND operation between two variables so that we can later use AND operators in our high-level programming language. Let's assume we have the following instruction sequences, which were found by the constructor. He might rearrange them in the following way and chain them together to construct the following gadget. So what we can see on the right side is, where is my pointer? This is the pop ECX batch instruction sequence. I omitted the return instructions on the right side for the sake of readability, but here you can see this is what actually will be on the stack in the end. So we will have a address to this instruction sequence over here, and what it does is it loads, it pops a constant into ECX, which is on the stack. So here we have the return address, and in the next field, we just put the constant that we want to load into ECX. In this case, this is just a blank line. And what happens then is we have a dereference, which is we load into EDX the memory being pointed to by ECX plus 7C. So what we can do with these two instructions is we can load memory values into registers. And we do that twice because we have a operation with two operands. So we do that again with EAX. We pop a value into EAX and then dereference this. And then we, assuming we found such an instruction sequence which performs an AND between two registers, we now have the result in EAX, and what we then do is we just write back that result into another memory variable. So this is just a nice example for how we can, how the constructor actually constructs an AND gadget. And this is a real example which was constructed by the constructor. So let's just skip over the nasty details and talk about the compiler. Here you can finally see some sort of real compiler code. As I said, this was all done in a dedicated programming language because there were some tweaks that we faced in which are very specific to return-oriented programming. So we thought that it might be wise to implement our own programming language instead of simply modifying an existing compiler of, let's say, a C compiler. But in the end, it all looks quite like C code. So what we have here is we have a import statement, which means that we can actually import functions from external code. So in this case, we just import the printf function from MSVCRT DLL, which is the C standard library under Windows. And the cool thing now is that we can now actually call this function, this external function. So what happens in the first line is that it simply prints out a hello world statement on the console. And the reason why we have actually implemented these external function calls is that in the case of the kernel exports the entire C standard library. And we definitely do not want to implement, let's say, string copy all the time in our rootkit. So why would we want to implement it when we can simply find the same code in the already existing kernel? So what you can do is you can really call external code. This is kind of cool. You can declare custom variables such as integers and stuff like that. We have integers, characters, and structures as our three basic, basic data types, you can just declare them as you would in C or C++. And what you can also do is you can have arbitrarily complex expressions, such as in the last line where you have an I plus j multiplied by 3 and stuff like that. So this is a more complex example. This is an actual implementation of quicksort in our programming language. So what you can see on the top is it's not the entire code. I left out one function because that would have been too much code. But what you can see is you can actually do stuff like recursive function calls in our language. So you can actually call quicksort from within quicksort. You can declare functions, how much function you want. You can simply call external code. I already showed you that. You can have while loops. They can be arbitrarily nested. You can have arbitrarily nested conditions. You can have combined conditional expressions. So it is very obvious that this is really a really comfortable way to program code, and this is not far away from just normal C programming. So now we are actually able of formulating our rootkit in a decent high-level language. And here's just another example on how this actually looks like in memory. So this is the compiled quicksort. These are the stack allocations. So the stack pointer in the end will point into some of these elements in memory. What you can see is that we have most of this is simply these are return instructions, addresses to return instructions. Many of them simply reappear because we always need some instruction sequences to load memory values into registers and stuff like that. And in between, you can also find some constants, which are the values that you need to pop into the registers. So this is how the real final return-oriented code actually looks like. So just one thing about the loader. I told you that we need to resolve the base addresses in the final stage because we need to know where drivers are loaded in the memory. And luckily, this in the beginning, I thought that this could be quite a big problem because we need to do this from the non-privileged code because we need to prepare our attack from the non-privileged area. And since we do not have access to the memory regions in which the drivers are loaded, I thought that it might be hard to actually guess the final addresses. But fortunately, under Windows, we have this standard enum device drivers function provided by Microsoft. And what this function does is it simply returns all loaded drivers with their base addresses. And you can call this function from even non-privileged code. So in this case, we really had no problem. And interestingly, it also works under Linux, because under Linux, you can simply do a cat on, I think, /proc/modules or something like that. And it would also return the base addresses of all loaded drivers. I don't know why they implemented this, because I don't see any situation in which you really need to know the base addresses of loaded drivers in non-privileged code, but hey, it's just there. So before I show you the real rootkit that I programmed, just some stuff about statistics. Talking about the constructor, the interesting question now is that is the constructor capable of constructing all necessary gadgets for the code base in which we work with? Because, as I said, the constructor, it works with certain simplifications and assumptions. And what we did is we tested the constructor on 10 different machines running different Windows operating system versions. We did this twice, once with the full code base, which means that we let it run over the kernel and all loaded drivers. And in the second turn, we only considered the kernel file itself along with the Windows 32 subsystem driver, because these two components always have to be loaded in the system. You definitely have to have a kernel in the system, and you definitely need a Win32 subsystem driver in your Windows system. And yeah, the results were kind of good, if not perfect, which means that in all cases, the constructor was capable of constructing all necessary gadgets. And if we have all necessary gadgets, we can use all the functionality as provided by the programming language. So just some statistics you can find here. In case of, in the restrictors case, in a native XP Service Pack 2 environment, you have around 22,000 return instructions, and that is about enough to actually construct all necessary gadgets. Another thing that we measured was the runtime overhead of programs, of return-oriented programs created with our framework. So we implemented these two different versions of quicksort. That's why I showed you the quicksort code. We did this in C and in our return-oriented programming language. The algorithm is, of course, exactly the same. We let it sort 500,000 random integers, and the result was kind of significant. So we had a slowdown by a factor of 135 for our return-oriented programs. I don't know why this is the case, but I assume that it has something to do with caching optimizations, because as I showed you in one of the previous slides, normally code gets executed sequentially. You have some jumps in your code, but you have some sort of code locality. And but with return-oriented programming, this is really different, because you have instruction sequences at very different memory addresses, and you always jump from between them. And I think that this might break certain caching assumptions. But anyway, this is slow, yes, but still, if you, let's say, program a rootkit, then you definitely do not have any time-consuming tasks, so this is not much of a problem for us. So let's come to the real rootkit example that I did. We now have an experimental setup of, we have a Windows XP system, we have a custom vulnerable driver, which I simply did from scratch. It's nothing special, it's just a driver that exports a certain file, which you can write to from user space. And when you write to that file, some buffer overflow happens, and we can now exploit this buffer overflow to execute our rootkit from user space. What it does is it traverses the process list of Windows and removes a specific process within that list so that we can hide processes. And I'm not going to show you the entire code, but this is just the part of the rootkit that actually unlinks this element from the process list. So what we have is, here we can call the external Windows function, which returns the head pointer to the process list, which is ps-get current process. And then we just have this while loop in which we traverse the list and search for an entry by the name of ghost.exe. And if you find that entry, we simply unlink it by switching the pointers of the nearby elements in the list. And if you have done that, then the process is effectively hidden. So these attacks have been shown in many different, have been explained in many different books, tutorials, and all stuff like that. So I'm not going to talk about how you can actually program your rootkit. So let's come to the demo. I've prepared a VMware XP workstation. I hope this works. I can't see my pointer. So, okay. No. Maybe I should have brought my glasses. Okay, let's jump to VM. This Ghost. Okay, so what we have here, this is the Ghost process, which is just a simple process that does nothing but increment a number and then print it out on the console. And if we now fire up the task manager on the right side, we can see that the Ghost process is somewhere in there. I think it's this entry. So it's shown up in the task manager just as every other process is shown in the task manager. And what I'm going to do now is I'm going to load rootkit. I'm just going to see which one is the right. I'm going to load a batch file which loads the driver in the system, and then exploits the vulnerability from within the user space and hides our process. So this is pretty fast. That was it. What you can see now is that we now have the Ghost process running. It still increments the number and prints it out. But on the right side, you do not see the Ghost process anymore. So it's completely hidden. And yeah, we have done that without executing any own instruction. So this is one example of a rootkit. I also implemented another rootkit, which actually hides network connections, and which, that is maybe the most interesting point. Why doesn't it show up? Why doesn't it show up my presentation on the right side? Okay, I think that's it. I hate it. Okay. yeah, that's the first rootkit. I also did a second rootkit, which actually hooks into the control flow of a system call. So this was kind of hard because there were really many technical problems that needed to be solved, and I had about 2 months of blue screens on the Windows, but in the end it actually works. So that's an interesting thing. It's really possible to hook into a program flow. All you need to do, I mean, we cannot overwrite any code, we cannot patch into the code, but as long as we have one pointer which points to a function that, let's say, handles the enumerations of Windows sockets, which is the fact, then if we just overwrite this one pointer, and along with certain kinds of gadgets, we can hook into the control flow and we can tamper with return values and actually hook all sorts of stuff. So now that I showed you how it works, I think I have to tell you how we can defend ourselves against it. So in the end, what I didn't tell you until now was there is a thing called address space randomization, which you probably know, and this is somewhat of the return-oriented programming killer. So the problem is that what I said with the loader, that if we had not this enum device drivers function, then our entire attack would be significantly harder and really unreliable, because we would have to guess memory addresses from the outside. And if we have a decent implementation of address space randomization, then this would be kind of impossible. Since we only have one shot, we only have one try to load our rootkit into memory, and if it doesn't work, we will be detected. So it is a cool thing, but I think in the end it's a somewhat fragile approach, and there are certain countermeasures against return-oriented programming. In the end, these are just the same countermeasures that you can see with return into libc functions. So let's come to the conclusion. We've seen that return-oriented programming is not just a theoretical thing. It is actually possible to create real return-oriented code just as comfortable as you can create any other code. And we have shown that it is actually possible to have an automated gadget construction, and that the number of code that we have within the memory which you can abuse is usually so big that it's not a huge problem to automatically create these gadgets, even by using very simple assumptions. And in the end, the final thing is that what has already been shown in the keynote is that the actual problem that we might have in a system is not malicious code, but it's malicious computation. And detecting malicious computation is a way harder task than detecting malicious code. Okay, that was it. Thank you for your time, and I'm happy to take your questions.
Ralf, thank you very much. Interesting talk and yet another demo. So I have one question. Yeah. Will you publish your framework?
Yes, it would be possible. Yeah.
Thanks.
I was thinking about that for half a year now, but I really didn't have the time to do it. But yes, I think it might be the right time to publish it.
Yeah,
you know, I think it's already
people
working.
People will be curious to play around with it.
Yeah.
So, okay. Other questions, please?
So my first question is on, if I understood correctly, what you basically do to push to keep all stacks forward on the stack.
Yeah.
So is the amount of space, the amount of memory you may have used to vulnerability?
That's a good question. But that's not a real problem. You are right. You normally on the kernel mode you have a limited amount of stack, which is on the Windows you only have a few kilobytes. I think you only have 2 kilobytes on the real stack. But what we can actually do, and what I did what the demo did is, you just can install a small stop at the beginning, which allocates memory in the kernel somewhere else, copies your code to that location, which can be arbitrarily big. And then you just move the stack pointer to that location, so it doesn't have to point to the actual stack location. So you can simply bypass this by just using a small stop, which then allocates bigger regions of memory.
All right, so my second question, if you don't mind. Could you elaborate a bit on conditional jumps or something like that? How do you do that? Are there special gadgets for that?
Yes, there are certain. Okay. Of course, you have this compare instruction on x86, but it only modifies the flags. So what you need to do is you have to do the compare instruction, and then you have to read out the flags from that flag register. And you can do that by, there is one instruction, which was the right, I think it was LAHF, which copies the exactly these flags into the EAX register. And what you can do then is to implement an AND operation. What did I do? I think you simply, if you have an AND, you simply do the AND operation. If you have a conditional AND, you simply do an AND operation between the results of both operands, and then you can take this result as an index into a jump table, let's say, and then you set the stack pointer to that jump table. That's what it actually does. I can show you better later if you're interested.
Okay, so another question, please.
Yeah.
When you're scanning for opcodes, are you looking at all addresses as the potential for tuning up the instruction sequence, or just the places that would be found by an ordinary disk system?
It looks for everything. It just scans for the region opcode, and then it looks backwards. So it will find all instruction sequences. Yeah.
Okay, please. No.
Is it possible to break out of the virtual machine or a best operating system to the host operating system?
If you have a vulnerability somewhere in your hypervisor, then yes. But normally it's not possible. It's only possible if there is some sort of vulnerability. If you can communicate with your hypervisor and then, let's say, override a buffer there. But it's not possible unless you have any bugs inside that virtualization code.
Okay, more questions? I think there will also the possibility to talk with Ralf in one of the breaks. So Ralf, again, thank you very much.